So I hope everyone can hear me. I just want to say a couple of words and hand it over to Kevin for the technical part of the presentation. But it's great to see you guys. It's absolutely fantastic. And we're sorry we can't be there. And but we did the best we can do. The next best thing we can do is wake up at 5 a.m. in our little town in upstate New York and chime into your lovely Italian town. So it's great to be here. And so I wanted to say one critical thing, because as you well know, a certain person is at least shadowing me on wherever I go and keeps saying things like, Emin, how well is he committed to Bitcoin or whatever. So we are talking to you today as Avalanche people. But at the same time, we're not just Avalanche people. I'm also a Bloxroute person. And Bloxroute, the very existence for that system is to target and provide a relay network for Bitcoin Cash. That's how it came about. I was worried that the Bitcoin relay network was going to get shut down and Bitcoin Cash might get stranded. And I'm also, and Kevin also as well, is a scientist to a fault. So we're also scientists, and to us, the most important thing is the truth, and that's exactly what led us onto this journey. And as you well know, I think I was one of the very first people calling out the disinformation campaign from various actors in the cryptocurrency space, way before the fork and way before anything else. So we're very, very sympathetic to making this particular approach work, and today. You all know about Avalanche, I hope, but if you don't, Kevin will give you an overview, and we'll talk about an interesting deployment scenario for Avalanche, which is how do we take it and combine it with a POW coin? This was one of the very first things we thought about when the idea came to us to deploy it in real settings, and so Kevin will do the actual technical presentation.
Sounds good. Okay, thank you guys for having us. So again, it is quite early out here. We are a little bit disoriented, so apologies if we sound a little bit off. I will try to speak slowly just so I can get the words to go through the video and nothing kind of breaks off. But let me see now to share the screen. Give me 1 second. Okay, allow. Okay, can you guys see the screen? Yes. Fantastic. Okay, so the talk will be really exactly what Gün just mentioned, using Avalanche for pre-consensus on Nakamoto Consensus-based protocols. Now, a little bit of an introduction. Nakamoto Consensus, again, is the security is 100% dependent on the underlying proof-of-work chain. By definition and by construction, and despite what other assumptions you may make, the probability of safety of a transaction is really exponential in number of confirmations. No matter what you do, if you do not use any further new modifications, then you're really relying on the number of confirmations in the chain to guarantee security. And in fact, depending on the Byzantine presence in the network, this number of confirmations can actually increase. And I had this a brief Twitter post about this, where as you approach 50% of the Byzantine presence, the number of confirmations required to be safe against a double spend actually increases asymptotically. At 50%, there is no known solution. You need to wait for an infinite number of blocks before you can accept a transaction. That's the theoretical result of Nakamoto Consensus. So basically zero conf implies mathematically by the protocol itself, zero probability of safety. Does this mean that zero conf is technically impossible in all scenarios? Well, no, not quite. Under basic and reasonable assumptions, is actually quite possible. And here's what we're going to talk to you about. And at a very high level, we're going to layer the current Nakamoto transaction commitment model with a mechanism really that provides some sort of pre-consensus is a weird word, but it's the closest I can think of. It provides some sort of a pre-consensus. It requires a soft fork with majority of miners adopting the protocol, but that's okay because we believe that this is it's very reasonable given the benefits that you're going to get. Now, this is one construction that we're going to provide, And it's not necessarily the only one using Avalanche. In fact, you can further improve the protocol that we're going to provide to you today to also increase throughput. But predominantly, we're focused on zero-conf confirmations for certain transactions in the system, and then future work we'll maybe talk about throughput as well. Okay, so what is the current Nakamoto commitment model? A transaction by a user is sent to a bunch of miners. Eventually, the miners will check the transaction and then place it on the blockchain. Eventually, after a certain number of confirmations, the client can see the transaction is buried deep enough, and the client can commit this transaction. Now, the way you would adopt, or rather go from a proof-of-work based system to a system that requires some form of identity management is you create basically a pre-agreement, soft pre-agreement on the set of miners by signaling whether miners will accept a certain transaction or not. And the new model basically looks like so. The transaction is sent to the miners. The miners amongst themselves first, very quickly, within a few seconds, are able to decide whether this transaction will be included in the next block or not. And remember, the assumption here is that the majority of the miners have soft fork it to use this new protocol. And then the client can immediately, if the client sees a threshold set of signatures from the miners that this transaction will be included in a particular block, let's say block N, then the client immediately accepts. Eventually, the transaction will be placed on the blockchain, and because the miners that are signaling commitment are greater than some percentage majority, and you can set this up as high as you want. For example, you can say that 60% actually agree on this, and this is verifiable using Avalanche. The higher this percentage agreement is, the more likely the transaction will be placed on the blockchain in the particular specified block using the protocol. If you get close to 50%, there might be some attack that can happen for some period of time. But the higher it is, and this is measurable, then the more sure you are of the transaction being committed in the blockchain. So now this middle part here, how do you achieve basically almost nearly instantaneous commitment without using crazy new methodologies in a network of potentially thousands or even millions of miners? And remember, you don't have, suppose you don't have pools here. You have individual mining nodes. Well, the basic idea is you use Avalanche. And what is Avalanche? It introduces a fundamentally new mechanism for building BFT protocols. So it's not really an incremental improvement over classical BFTs like PBFT and Tendermint and Ripple and et cetera, even Algorand, for example. It exploits a mechanism inherent in epidemic networks where simple gossiping pulls and pushes in the network actually provide a strong toppling effect of where everybody moves over to a particular proposed value. So nodes sample almost a nearly constant size set of neighbors, and again nearly because it's not exactly constant, but it's for all practical purposes is basically constant. And then repeat this step for a logarithmic number of rounds. And eventually, after this number of messages, we all converge to the same proposal. Very basic visual representation of how this works. So you have this node over here. It doesn't have a proposal yet, is in black. But these nodes its neighbors have red and blue. It samples these neighbors and selects a simple majority, and then it becomes red itself. And basically, this process is repeated in parallel amongst all nodes. And turns out that this sort of mechanism is robust enough that, again, as I said, in just a few rounds, we're all going to converge in the same value. So it's extremely fast and efficient and lightweight. Using the core mechanism, you can actually amortize the cost of the logarithmic number of rounds into just a single sample for every single transaction. So basically, you get a total cost of O of 1 per transaction in the system. Now, remember that this per single transaction complexity is still unchanged. We're still only amortizing the cost, but effectively, this is what you get over time. So what are the properties of Avalanche? It's extremely fast and lightweight. As I said, it brings around complexity to O of 1. scales to thousands or millions of nodes. And then lastly, it does not need precise membership. This is a very important feature that differs from more classical style protocols like PBFT, where you have 100 and you require precisely to know exactly these 100 nodes, and then you require a specific threshold to agree, in this case for PBFT, 2/3 on a proposal. In Avalanche, no such requirements. You can have discrepancies in the views of the nodes up to a certain threshold. You can actually set yourself the required threshold for agreement that you would like. You can set it to be 60%, 70%, 80%, and so on. And the higher this threshold is, it will impose a little bit of round complexity to the system and message complexity, so you will require a little bit more work to do, but still it's going to be very fast, yet you're going to have much, much stronger security guarantees. So it's a very tunable knob that it provides in comparison to other protocols. So Avalanche for pre-consensus, the protocol, very high level. The client sends the transaction to the miners. Within 1 or 2 seconds, the miner either approves the transaction for block N or rejects, and the client itself does not need to rely on a single miner. It can actually do this verification itself. It samples the network exactly the same way that the miners in the network would. And then, if approved, the transaction will eventually appear on block N. Some transactions will not be included in block N. And the reason is because, well, we have only limited throughput per block. And of course, if you have thousands and thousands of transactions coming in for block N, some of them will not be included in block N, and therefore will need to wait for confirmation in block N+1. And so these kinds of transactions will not get nearly instantaneous commitment. So they will require waiting until the next block. Okay, so conclusion. We have incomplete, but foundations are there. Avalanche provides latency in 1 or 2 seconds. Throughput is completely unaffected. Implications is that not all transactions get instant confirmation. So how do we get to get all transactions to get instant confirmation? We basically have to work with the throughput to get the throughput to go much higher. Now that will require, unfortunately, more software.
Hi, thank you for that. Yeah, I do have a question. Like, roughly, if you look currently at, we assume very efficient block propagation, then basically the total amount of bandwidth that we use for a transaction is only the size of the transaction plus the size of an inventory message per connected pair for everyone. And I'm assuming hereby there's going to be more cryptographic data needs to be sent back and forth. What would be an estimate of the total amount of extra data requirements that we're looking at per transaction?
I'm sorry, I actually could not hear you quite well. Can you, do you want to repeat? Or maybe
I got it, I think. I think the question, if I understand it, is the amount of extra communication requirements. Is that right?
Yes.
Yeah. So I think it's simple to say that it's quite modest. So Avalanche is here. Let me try to give you a very short redux of what Kevin said. So deep down, what he's suggesting is there are sort of certain ways in which people think Bitcoin works, but it doesn't work that way. Bitcoin really works by electing somebody and having that guy dictate. And Kevin's saying, look, before that phase, why don't you have the guys who mine participate in a very short pre-consensus protocol, and in that protocol select the content that's going to go into the next block. And the way, by virtue of the way Avalanche works, those people will have to be miners, and it's going to be a democratic process. Every miner gets a voice, and they pick which transactions go in. And that particular process, so there's one catch that may or may not have come out. Avalanche is really designed for really large networks, and the Bitcoin miner network is rather small. So I can give you numbers for really large networks, and maybe Kevin can give you numbers for very, very small networks. But for large networks, let's say you have thousands of nodes and you want to reach consensus. What you'd have to do with Avalanche is essentially sample a very small set, say 5 nodes or so, for a very small number of rounds, say 13 to 15 or 17, I think is the number for a really large network. So that gets you something. I think the numbers that I'm giving, 17 gives you like 50,000 nodes, and 13 gives you 1,000 nodes or something. Am I right, Kevin? I'm
Yeah,
kind of speaking, approximately speaking.
yeah,
So,
it grows very little. Yeah.
it grows very little. So the number of messages sent by a node to achieve consensus among a very large group is very, very modest. You're not asking everyone else. So it's not like every miner is talking to every other miner. You're subsampling. You're creating this avalanche effect. So imagine that you're in a stadium of 50,000 and you're sending 85 messages, right? That's what 5 by 17 is 85. So 85 messages gets you that pre-consensus or that consensus that you need. So it's very, very modest.
But that's what you do per transaction.
And we need to do that now. Yes, Laurie, go ahead.
And it is kind of per transaction, right? For the one who wants to know the consensus. Okay. Yeah. Okay. Thank you.
Any other?
I didn't get the last sentence. You
No, I'm just from my understanding, we're talking about this pre-consensus is done for each transaction, but then only from the one who wants to know the certainty.
In this model, yes, you can certainly batch transactions. I was for simplicity, saying per transaction only, but certainly you can batch transactions. There's nothing preventing you from batching them.
Okay, yeah, thank you.
Kevin, can you do something where it's actually done only when you have a conflicting transaction? I don't see why not.
But then you don't quite know when the conflict transaction will be detected in the network. There's kind of like a chicken and egg here, yeah. So.
All right, so
yeah, there are conditions, but it seems like the simple thing is you do it on a per transaction in some batched manner.
Yeah.
So thank you very much for the talk. My question is more about how you are thinking about knowing that it was a minor membership. So how do you prevent people that are non-minors from doing the vote, and how do you tie the votes to guarantee it was actually a minor that actually provided the vote?
So that's a very interesting question. And to repeat, I believe the question is, you guys are coming through a little muffled. So
Yeah.
the way I heard it is that you're asking how we prevent people who are not minors from coming in and messing up the entire process. So that's a great question, very, very insightful question. The lovely thing about having the proof of work blockchain behind the scenes is it gives us security, right? Things that are committed there, people understand that process by now. People are committed in Bitcoin to the security of the blockchain, the effort that went into mining those blocks. They understand the energy that went in. That also gives them a sense of value as well for psychological reasons. And so that's all great. But B, it also does something else. It allows us to identify those nodes that have hash power. So a very simple thing one can do is provide proof of having mined in the recent past. So if you have hash power and you've mined a block in the last, say, month, then you get to be a miner for the definition of participating in the pre-consensus protocol. Now, one might still want to, if one wanted to make noise and create sort of reasons to reject this idea, one could say, oh, but that's not egalitarian. What about me on day one? Then I can't participate. Well, that doesn't prohibit you from actually participating in the mining and earning of reward. So that is, suppose I'm a brand new miner and I just turned on my machine and I have no blocks to my name whatsoever. Okay, then I still get to listen in to the pre-consensus. I still know exactly what to mine. And when I do mine things, my blocks will still be accepted. And as soon as I have that first block, then I have the necessary proof for being able to participate.
So that makes a lot of sense. When there's, I'd love to see a spec on exactly how they would notify that they had created that block in the past, but that's exactly what my thought process was. So as you get more specs on exactly what that looks like, I would love to see those.
Okay.
I'm not sure I got the last sentence.
I was just saying that when there's an official specification on what the miner needs to do to prove that he has mined a previous block, I would be very interested in the research on how that would actually be implemented. So when that is available, feel free to reach out to me.
Right.
I'd just love to look at
Yeah,
that.
we don't have an official spec yet.
Yeah, there's no official spec on that front.
Yeah, but absolutely.
But I want to very carefully emphasize this. Nothing that Kevin described requires a sense of identity for minors. And also, there is absolutely no censorship vector here. So a minor cannot censor a transaction just because. Like, if I'm spending some money to Alice, then it's not the case that the minor can say no to this. The Avalanche process will necessarily okay that transaction.
Yeah.
This is only, the decision process can only pick between conflicting transactions. So if I spend a double spend, that's the only time that the minors get to say red versus blue. So if I spend to Alice and to Bob the same UTXO, that's when this process gets to have some decision pattern. Otherwise, it's the defunct process. You ask people, they say, yes, I know that transaction, and then at that point they accept it. So
and that's fundamental property of the fact that there's no leader to elect a transaction at any particular block. If a transaction is available to be placed in a block, it will be placed in the block, and the network will converge to it.
Right.
So I have two questions. The first one is, can you talk about the incentive structure a bit that arise when a miner decides to disregard Avalanche and mine a block that contains something that doesn't comply with what was decided by Avalanche? So what do you do? Do you orphan the block, or do you accept it anyway, or like what's happening there? So that's the first question. The second one is, have you considered to have other set of participants in there, such as, I can imagine a big payment processor or large exchanges, or like generally big business in the space would be interested in participating in that consensus algorithm?
So I think the first question was, what happens if a miner decides to mine a block that goes against the Avalanche protocol? Is that correct?
Yes.
Right. So under the assumption that the set of miners that do such a thing are a minority, they will be orphaned over time. Of course, if it's like 50-50, they will never be orphaned. You will always have, like, theoretically this equal generation of blocks. But if it's a minority, then it will be orphaned pretty quickly.
So I think the simpler answer is this should be a soft fork, and if it's a soft fork, then people who don't obey the protocol will get their blocks orphaned. Now we can soften this a little bit. We can make it a soft fork or something like that, soft cubed fork, in the sense that if you mine a block and there are transactions in it that the Avalanche or whatever the pre-consensus protocol has not seen, then no harm done, and that's okay too. It's only a problem if the pre-consensus protocol indicated to the world that Alice was going to get paid, and then you went ahead and mined a block that's the opposite. In that case, you're a malicious miner, and you've now mined the payment for Bob instead of Alice, and everybody else was expecting for the last 10 minutes that Alice was going to get the cash. So you're doing something really hokey and bad, and in that case, the hash majority should not respect your block and say, look, this was you did not do this properly, and we're going to have to reject this and go back to our strong guarantees for zero count transactions.
Yeah, and what was the second question, by the way? I wasn't able to follow.
Okay, yeah, so first question, great answer. The second question is, so you need a Sybil-resistant mechanism for Avalanche to participate in Avalanche, and you guys are proposing to use proof of work for that, so that miner can participate. And what I wanted to ask is, have you thought about using different mechanisms, such as maybe coinage or whatever else, so that other big network participants can participate? So I can imagine that a merchant processor like BitPay, for instance, would be interested in participating in such protocol.
So the question is, are there mechanisms besides proof of work to use for Sybil
Yes.
protection?
Yes.
Well, I mean, there are proof of stake mechanisms, but not necessarily that you would need them in such a case. You could potentially use the underlying proof of work mechanism or the chain to get a sense of who the miners are.
Or put differently, yes, absolutely. There are many different ways of doing anti-Sybil mechanisms. In the Ava coin we are building, we are exploring proof of stake. But if one wanted to use this with Bitcoin Cash, the way to do it would be to take advantage of the lovely blockchain and the POW mechanism underneath. So stake has some benefits on top of proof of work chains, right? If you use stake entirely and you switch to Ava coin, it has a bunch of other benefits. In particular, there is no energy expenditure. You get rid of the miners entirely, and there is no leak of value from the system, etc., etc. I could go on to describe why Ava coin, I think, has some amazing features as well. But Bitcoin Cash community, they love the mining. It's like the users are, they understand it. This is what people like. And cutting out the miners, I think, is the non-starter for this particular application. So if you wanted to use Avalanche for pre-consensus, you would take advantage of the existing POW.
Okay, thank you.
You would not introduce any other complication.
Okay, thank you. We're moving on to one final question.
I'm just curious if this would effectively kill SPV mining.
I already can't hear you. Sorry, can you speak up a little bit?
Sorry. Would this disable SPV mining? As in, would it be impossible to mine empty blocks?
I cannot hear.
I think the question is about empty blocks, Kevin.
Oh, okay. What? Okay, yeah. Go ahead.
Would this disable mining empty blocks?
Are you asking, are empty blocks allowed to be mined?
Yeah.
Certainly, yeah, certainly, sure. If that means the empty transactions are required to be placed in the block and agreed upon by the pre-consensus.
I think in general, there are many good reasons to allow empty blocks. Miners have crashes, their databases get out of sync, they find themselves in a bind, they are not going to turn off the guys. Anybody who's ever rebooted a miner knows how stressful that is for the machinery as well. So it's a dumb idea, I think, to try to get rid of them. And I think it's okay to have somebody mine an empty block. That doesn't cause a merchant to lose money.
I agree.
If you really wanted to, view that, and generally empty blocks help the confirmation process. They help the security of the network. SPV mining is something I'm actually a fan of. It's actually good for the network. So all of those things are fine, and I don't see a big problem with them. In some circles, sometimes people get really upset. And I think in the Bitcoin Cash domain, one does have to worry about some kind of a bad miner who persistently and for a very long time mines empty blocks. And if you guys are worried about that, one could potentially come up with mechanisms to fix it. That will be independent of the pre-consensus mechanism. So I'm happy to have that conversation as well, but it has very little, in fact, nothing to do with pre-consensus. So fixing that issue or that vulnerability, if you will, it's something we can contemplate. Luckily, it's something we haven't seen, even though Bitcoin Cash is only, 6% of the main Bitcoin hash rate. We can contemplate it, we can explore it if you like, but it's completely independent of Avalanche.
Yeah, and to kind of give some summarization, what the pre-consensus gives you is for certain transactions, whether that transaction will be placed in block or not, and it gives you quick finality for that question. There might be other empty transactions placed in the block, and that's okay because you don't have to agree on those. But as long as you agree on the actual transfer of ownership transactions, then that's fine. More question?
Yeah, 1 second.
what do you mean with empty transactions? What's the definition?
I mean, just fill up the block. So you can have Alice pays Bob, one transaction in the block for block N, and the rest can all be empty. If there's no more confirmations.
You guys have to understand that Kevin is kind of a mathematician, so
Yeah,
he uses
that's-
words that are slightly different than the standard terminology. So Kevin, there is no such thing as an empty transaction.
Okay, well, I'm just saying you can fill it up with empty bits. Is like I don't know
Yeah,
exactly
got
how
it, got
to
it.
fill
Yeah,
up.
got it.
Empty
Thank you.
bits. Yeah, we got
Yes.
it. We got
Okay.
it. Okay.
Yeah.
To the rest of the world, that's an empty block, guys. It's
Okay.
Okay,
Thank you.
thank you very much again to the two of you for getting up this early in the morning. And
Absolutely.
should we give them a round of applause
our
again?
pleasure, guys. Our pleasure. We're sorry we can't be there.
Thank you. Talk to you guys.
Enjoy Italy. Take care.
Thank you. Bye-bye. Bye-bye.
Thank you.
Bye, guys.